All right. Let's see, what do we got today? We have double integrals in polar coordinates, and we have rectangular triple integrals. All aboard the Polar Express. If you don't remember, that is a Christmas movie, animated. So we are going to evaluate double integrals in polar coordinates. Let's first recall our conversions. Yeah, so these are from, we did this in Math 2414, and we touched on cylindrical at the beginning of the semester, but polar is just cylindrical in 2 dimensions, or cylindrical is polar in 3 dimensions. So here are conversions. We know x is equal to r cosine theta in trigonometry. Same thing with y equals r sine theta. And r squared equals x squared plus y squared. That's just the Pythagorean theorem. So converting double integral in xy coordinate system to a double integral in polar coordinates. Let's look at what we have to do. So if f is continuous on a polar rectangle R given by the radius lies in between a and b with a greater than or equal to 0, and theta lies in between alpha and beta with the difference of beta minus alpha lying in between 0 and 2 pi, then the double rectangle, or the double integral over r of f of x y dA is equal to, and we have this animal, the double integral from alpha to beta, a to b, f of r cosine theta. Since we have x, we have replacing it with r cosine theta, and we have y, r sine theta. And then the differential element, dA, actually turns into r dr d theta. Now, you might be asking, where does this rogue r come from? Well, that I don't think they will actually get to in this class, but if you want to do some research over why there is a an r converting from rectangular to polar, then I would forward you to let's see, it's the change of variables section in Stewart's calculus book. So this is be 15.10. But basically, what we have going on is a generalization of u substitution to functions integrals of multiple integrals, and it's called the Jacobian. So the R comes from the Jacobian matrix. Basically, you have a single integral from a to b of f of x dx. This, if with the proper substitution, integral from c to d f of g of u times u prime g prime of u du. It's like this g prime of u is what that r is in essence. But hopefully we get to that in this class, because I like, you could do some really crazy things with it. You can, you could have a region in R2 you're integrating over that is neither type 1 nor type 2. Look at this region. So this region If I try to do vertical cross sections, look right here, different roof than over here, different floor over here. So I would have to split this up into, oh wait, this actually is type 2. Oops. Because you could do horizontal cross sections. Look, you could do horizontal cross sections right here. So that's not a good example. I would still work on that. But we could do, okay, I have a good one actually. We have, yeah, this animal right here. So like a trapezoid, like this. Yeah, see, this is neither type 1 nor type 2, but with proper substitution, anything is possible. Well, maybe not anything, but we could integrate this a lot easier. So let's look at what we have next. Yeah, so this was over, this top one was over a rectangle. But we can do it over more general regions in polar. So you notice that what theta lies in between alpha and beta, and r lies in between a function of theta and a function of theta. So that would look like, well, okay, so theta is constant, alpha, beta. Then we have r, the radius, the distance from the origin, a variable of theta. So we could integrate over something like that. I don't think I have any examples like that. But what I have, I think you will find of interest because they're quite similar to the homework problems. And I actually found this out of the book, page 1002, number 8, where R is a region in the first quadrant enclosed by the cylinder x squared plus y squared equals 4, x equals 0, and y equals x. So let's draw this. What do we have? That's not a cylinder, that's a circle. This is an R2. It's a region in R2. So we have x squared plus y squared equals 4. That's a circle with radius 2. We have x equals 0 right here. And we also have y equals x. So let's do this in blue. Y equals to x. Ooh. 45-degree angle, right? Bisects the first quadrant. So R is a region in the first quadrant enclosed by x squared plus y squared equals 4. Here. X equals 0. That's the wrong x equals 0. X equals 0 is really what? That's really the y-axis. The vertical line. And then our circle. So it'd actually be this region right here. This is R. Okay. Well, so we want to integrate R over, this would be, some plane in R3, the 2x minus y. Look at that as like f of xy equals 2x minus y, or z equals 2x minus y. So let's set up this double integral in polar coordinates. The double integral to, remember, x is equal to r cosine theta. Y is equal to r sine theta. So we replace x with r cosine theta minus r sine theta. dA turns into r dr d theta. Okay, now we look at what r bounds. So the radius is going from all the way from the origin to the point 2, or the circle 2 in polar, because you look at x squared plus y squared, that's really r squared, is equal to 4. Take the square root. R is always positive, 2. So we're going from 0 to 2. Theta, on the other hand, we're going from pi over 4, the bisection, by the line y equals x, to pi over 2. So if you want to really get down to the polar, what's going on in polar, so we have y equals x. This relationship is this line. That's r sine theta is equal to r cosine theta. So r cancels. So we have sine theta equals cosine theta. In the first quadrant, the only value of theta that satisfies this is what? Theta equals pi over 4. So you could find it that way. And then the x equals 0, that's really r cosine of theta equals 0. This is true when theta is equal to pi over 2. Cosine of pi over 2, 0. So you can do it that way. Cool. So let's look at what we have. So we have the double integral 0 to 2, 0 to pi over 4, or pi over 4 to pi over 2, distributing the r through r. So we have 2r squared cosine theta minus r squared sine theta dr d theta. Okay. Well, this turns into what? So this is the double integral of the sum, right? We have two terms, is the sum of the double integrals. So I'm going to set this up as two double integrals, 0 to 2, pi over 4, pi over 2. The 2 can come out. We have an r squared. We have a cosine theta. We have a dr d theta. We subtract 0 to 2, pi over 4, pi over 2, r squared, sine theta, dr d theta. Now remember, a previous session, we came to the conclusion that if we have, double integral over some bounds, so say a to b, there's numbers, c to d, of f of x, g of y, dx dy. This is the same thing as c to d, g of y dy times a to b, f of x dx. So we have the same thing going on. We have separate functions of r and theta over, some rectangle, so we can just do the multiple, the product of two separate single integrals. Well, actually 4 separate single integrals because we got 2 terms. So that's what we're gonna do. Let me erase this so I have more room. All right. So what do we get? This is equal to 2 integral pi over 4 pi over 2 cosine theta d theta 0 to 2 r squared dr minus 0 pi over 4 pi over 2 sine theta d theta times 0 to 2 r squared dr. Okay, so this turns into writing it down here. Okay, so the integral antiderivative of cosine, positive sine. So we have 2 sine theta evaluated from pi over 4 to pi over 2 times 1/3 r cubed evaluated from 0 to 2 minus, so minus the integral sign, that would be plus cosine theta. The antiderivative of sine is negative cosine, and the negative negative makes a positive. Pi over 4 to pi over 2, 1/3 r cubed 0 to 2. And what do we get? You just have to plug in function evaluation. So 2 times sine of pi over 2 is just 2 minus square root of 2 over 2 times 2 is root 2. That times what? We have 2 to the third over 3. That's 8 over 3 minus 0, 0. Now we have plus cosine pi over 2 is 0 minus square root of 2 over 2 is cosine pi over 4 times same thing, 8 over 3. So what do we get? We have 8 times pi over, or 8 over 3 times 2 is 16 over 3. Then we have 8 over 3 minus times negative root 2, so that's going to be then another one of those. So we have, oh wait, that's different. That's over 2. So what do we get? I'm running out of room. Let's see. Copy and paste it at the very bottom. Oh, that didn't work. Well, okay. Yeah, so we have not enough room. 16 over 3 minus root 2 minus root 2, 8 over 3. So we have, if I'm not mistaken, we had 2 minus square root of 2 times 8 over 3 plus 0 minus square root of 2 over 2 times 8 over 3. This is 16 over 3 minus 8 root 2 over 3 minus, well, this 2 cancels with this, so this is 4. We have minus 4 root 2 over 3. 16 over 3 minus 12 over 3 square roots of 2. 12 divided by 3 is really 4, so we're 16 over 3 minus 4 square root of 2. That's the answer. So therefore, the double integral of 2x minus y dA over, r is equal to 16 over 3 minus 4 square root of 2. So that's the answer to this one. Okay. Find the volume of the solid above the xy plane within the cylinder x squared plus y squared equals 4 and below z equals x plus 2. Okay. So what do we get? We have the cylinder. Radius 2 engulfing z. That's the circle. That's the trace with the xy plane. We have a cylinder. Yeah. Above the xy plane, right? We drew the xy plane, and then z equals x plus 2. Well, what is that? We have x. We have z. Z equals x plus 2. So that would be 1, 2, 1, 2. This line, in R3, it's a plane. So But if you notice that the x equals 2, negative 2 is right here, and right here, and z positive 2 is up here. So it's really just like this guy, this line, and then we make him a plane. Where we have, yeah, like that. So we have above the xy plane, and then this region in R2 integrating through that, and then below z equals x plus 2. So you can draw the curve of intersection of this cylinder and the plane as like a rotated ellipse. It would look like that. Where this is like the negative 2, and this is, some part in the positive x. Okay. So yeah, it'd be just a rotated ellipse. Something like that. So we want the solid above xy plane within the cylinder, x squared plus y squared equals 4, below x plus 2. Okay. Well, in the xy plane, remember we have this guy. So we're going to be doing the double integral of z over a region R. So this is really what? This is the double integral R cosine theta plus 2 times R dr d theta. R is ranging from 0 to 2. Theta is ranging from 0 to 2 pi. Okay, so we get, let's see, we distribute the R, 0 to 2 pi cosine theta d theta times 0 to 2 R squared dr plus 0 to 2 pi times 2 d theta times 0 to 2 R dr. All right, this is not too bad. If we look at this first integral, I mean, we could do this geometrically, right? So cosine from 0 to 2 pi. Oh, okay, so at 0 we get 1. At 2 pi we also get 1. At pi we get negative 1. Pi over 2 we get 0. Pi over 3 we get 0. Okay. So that would just be 0 if I'm not mistaken. Because, okay, well, if we look at it, this is cosine. Integral of cosine is what? Sine. We get sine evaluated from 0 to 2 pi. Sine of 2 pi is 0. Sine of 0 is 0. This whole term goes to 0. Multiplied by r squared, this goes to 0 too. Well, 0 times, some number equals 0. Cool. So we don't have to worry about that first part. Now the second part, we have the integral d theta 0 to 2 pi is this, 2 times this 2 is this 2 times 2 pi times have r squared over 2 evaluated from 0 to 2. So we have 2 times 2 pi times 4 over 2. Well, 4 over 2 is just 2. 2 times 2 times 2 is just 8 pi. All right. we got page 1002, number 10. R is a region that lies in between the circles. Okay, so we have circles. A, radius B. So this is our region. And then what do we get with this? So convert this to polar. We get the double integral. Y squared is R squared sine theta. X squared plus Y squared is R squared. dA is R dr d theta. So R is in between A and B. Theta is in between 0 and 2 pi. Okay, so what do we get? We have these R squareds cancel. And then we can separate this out as 0 to pi sine theta d theta times a to b and then r dr. Okay, so sine of theta, the integral of sine is what? Negative cosine. Evaluated from 0 to 2 pi. And then times over to r squared, evaluated from a to b. Okay, so what do we get? We get negative cosine of pi, or 2 pi is 1, minus hold on. It's not looking right to me. Sine squared, that's it. This is sine squared. All right, that's not too bad. So we have, well, okay, so the integral of sine squared theta d theta is the same thing as the integral of 1/2 minus cosine 2 theta over 2 d theta, evaluated from 0 to 2 pi. Okay, well, 1/2 d theta is 1/2 theta. And the integral of cosine, is sine, so it keeps the sine, 2 theta over 4. 0 to 2 pi. So for this first integral, we get 2 pi over 2 minus sine of 4 pi, 0. So minus 0. Minus, and you plug in 0, you zero everything out. So this is just pi. And then we get times, r squared over 2, evaluated from a to b. So this is pi times b squared minus a squared over 2. This answer. All right, yeah, now we have this animal, page 102, 1002, number 13. Arctangent y over x, where r is in between 1 and 2, and then 0 is less than or equal to y, is less than or equal to x. So here's y equals x. And so y is greater than 0, but less than x. So I think it's this region right here. Okay. So this is, r squared lies in between 1 and 4. So that's 1 is less than or equal to r is less than or equal to 2. And then we already worked on this earlier. That was it's going to be 0 to pi over 4. It bisects the first quadrant. Okay, so we have the double integral of tangent inverse r sine theta over r cosine theta r dr d theta. R ranges from 1 to 2. Theta ranges in between 0 and pi over 4. Okay, well the r's cancel. So this is equal to 0 to pi over 4. 1 to 2. Tangent inverse. Sine over cosine is really tangent theta. R d theta. What is tangent of tangent? What is tangent inverse of tangent? Well, in the first quadrant, that's just going to be theta. We have 0 to pi over 4, 1 to 2, theta, r, dr, d theta. Okay. Okay, so we get theta squared over 2, 0 to pi over 4, times r squared over 2, 1 to 2. This is going to be pi squared over, let's see, we get 16 times 2 is 32, times 4, which is 2 squared minus 1, over 2. So this is going to be 3 pi squared over 64. We're making great time. I think we're going to finish super early. I just pull some problems out of the book. So we got a rectangular triple integrals. All right, yeah, so let's just recall what a triple integral does. So if we have the triple integral over e of 1 dv, this is equal to volume. It's the triple integral of e f of x, y, z dv. This is equal to a hypervolume. You can also look at this as a mass if f represents density. Okay? So we have this problem. We have the integrand is 6 x y. E lies underneath 1 plus x plus y above the xy plane bounded by this region in R2. So let's first draw our region. So we have square root of x. We have x equals 1, y equals 0. So it's this region in R2. And then, well, z is this plane. So if we draw the plane, what do we get? Okay, so when x equals y equals 0, that implies z equals 1. But if y equals z equals 0, x equals negative 1. And if x equals z equals 0, and y equals negative 1. So we have negative 1 on the x, negative 1 on the y. So we can see it's going to come up above the xy plane as the z-intercept is 0. And it's going to, shoot up like that. So it's, yeah, like that. Something like that. And then we have, of course, we have the region. So, right, it's engulfing x on the positive side. So it looks like this. We have y 0 and x equals 1. So it's above this region and below this plane right here. Okay. So what do we get? We got the triple integral over E 6xy, and let's do dz dy dx. So z ranges in between 0 and plane, 0 to 1 plus x plus y. Y ranges in between, now we look in the region R2, 0 and square root of x. And x lies in between 0 and 1. All right, so we integrate z, 0 to 1, 0 square root of x, 6yz, evaluated from 0 to 1 plus x plus y, dy dx. So this is equal to 0 to 1, 0 root x. 6xy, well, 6 will come out. So we have xy times 1 plus x plus y minus 0. So we have xy times 1 plus x plus y minus 0 dy dx. Okay, so if we want to distribute, what do we get? We have 6 integral 0 to 1 integral 0 square root of x. We have xy plus x squared y plus xy squared dy dx. So now we must integrate y. If we integrate y, we have 6, the integral from 0 to 1, xy squared over 2 plus x squared y squared over 2 plus xy cubed over 3, evaluated from 0 to root x dx. So this is 0, or 6 is 0 to 1. Plugging in x squared, or square root of x to y squared, well, we have the square root of x squared. That's just x. So we have x squared over 2 plus x cubed over 2, right? Because we have x times x squared divided by 2. This is plus x, and then we have x to the 3 over 2, and this is a 2 over 2. So really, isn't this just x to the 5 over 2? Because we have 2 over 2 plus 3 over 2, 5 over 2 over 3 dx. All right, now I just need to integrate this integral of one variable. So what do we have? We have 6, and integrating x squared, that's x cubed, and then divide by 2 times 3 is 6. We put x to the 4th over 8, because 4 times 2 is 8. Then we get plus x to the 7 over 2 times 2 over 7 divided by 3. That's 2 over 21, evaluated from 0 to 1. It's nice to give us that 1 and the 0. This calculation is super easy. So we have 6 times 1 over 6 plus 1 over 8 plus 2 over 21. And so this is what? So multiply, multiply, multiply. We get 1 plus, divide by 2. That's going to be 3 over 4. See, we have 12 over 21. Okay, so 6 is really, so we have 3 times 2 squared over 3 times 7. It cancels, so this is just 4 over 7. Plus 4 over 7. By 7 over 7, 4 over 4. 28 over 28 is plus 21 over 28 plus 16 over 28 is, what do we get? 28 plus 21 plus 16 is 65 over 28. That's the answer. All right, yeah, now we have this next one. So the solid enclosed by the cylinder, y equals x squared, and planes z equals 0, and y plus z equals 1. Let's see. We have the solid enclosed by the cylinder. Let's draw it. Well, you know, in the xy plane, we know what that looks like. That's just a parabola. So it engulfs y, goes on either side of x. It's a cylinder like that. That's a cylinder. And then we have z equals 0. That's down here. You know, this is the xy plane. And then we have z equals 1. Well, that's z equals 1 minus y. That's, well, z-intercept of 1, y-intercept of 1 goes like that. So it's that plane. So we have y-intercept 1. This plane. Z equals 1. So we want to do this as a triple integral. We're going to find the volume of it. So this is triple integral over E 1 dv. Let's do dz. C doesn't matter. I'm trying to think if we should do dy dx or dx dy. Because if we have x squared and 1. So this would be, if we do vertical cross sections, it would be x squared to 1 if we do dy. Yeah, let's do that. So we do dy dx. The y is ranging from, so first of all, z is ranging from 0 to plane, 1 minus y. And then y ranges from, let's see, x squared to 1. It's the y-intercept. And then x ranges in between -1 and 1, because that's what value gives us 1 when we square it. 1, 1. Okay, let's see if this is right. Okay, we have integrate z, get z, plug in our bounds. Now it just turns into a regular double integral to find volume. See, when we have planes like this, in between the planes z equals 0 and z equals, you know, some plane, and really you can just cut it down to a double integral, no problem. See, we're used to this. Okay, so integrate y, we get eta 1 to 1, y minus y squared over 2, evaluation from x squared to 1, dx, this is -1 to 1, 1 minus 1/2 minus x squared plus x to the 4th over 2. Plugging in 1 first, and plugging in x squared. Put the sign of the second part, dx, fundamental theorem of calculus. This is really 1/2 minus x squared plus x to the 4th over 2. Okay, so this is equal to 1/2 x minus x cubed over 3 plus x to the 5th over 10, evaluated from -1 to 1. So we have 1/2 minus 1/3 plus 1/10 minus -1/2 plus 1/3 minus 1/10. Okay, so we get 1/2 minus 1/3 plus 1/10 plus 1/2 minus 1/3 plus 1/10. Okay, so what do we get? We get 1/2 plus 1/2 is 1 minus 2/3 plus 10, 1/5. Okay, so this is equal to 15/15 minus 10/15 plus 3/15. This is 15 minus 10 is 5 plus 3, so this is 8/15. All right, so that is actually all that I prepared for today. Got through a lot of problems really quick. So let's do a little recap. Polar conversions, we know that. And then we can change this rectangular integral into polar rectangular integral. Rectangular integral, the polar integral, using r dr d theta over general regions too. This one is like your homework question, number 1A. This one is like your homework question number 2, number 1B. And this is just for fun. This one's also just for fun. And triple integrals, if there's an integrand other than 1, we get a hypervolume or maybe a mass if it's a density function. And then if it's just an integral of 1 dV, triple integral, then we get volume. Okay. So this first one found like a hypervolume. The second one found a true volume since the integrand was 1. All right, guys. Well, thanks for watching. And let's see. Howdy. Inverse. Goodbye. Goodbye.